This video is going to be on objects that are horizontally projected. So horizontally projected objects can either be objects that are, let's say, launched horizontally off of a cliff, or they can even be considered objects launched from planes flying at specific velocities. Okay. So in any case, whether you're being launched from a plane or launched off of the top of the earth or top of a cliff, what's important in these types of problems is to make an X direction list of things that you know and a Y direction list of things that you know. It's important to keep the two directions separate because they are independent of one another, meaning whatever happens in the X direction does not affect the things occurring in the Y direction. So let's take our cliff example, and let's say we know that the cliff is at a height h. Okay, so things we know in the X direction. Okay, well, that velocity that the object is launched at is going to be in the X direction because we're launched horizontally off a cliff, and horizontal means X direction. So we know that our initial velocity in the X direction is that velocity v, or the launch velocity. Okay. Now, the other stuff that we know in the X direction is assumptions that we have to make. So they're not going to be immediately given to us. They are just things that we need to know or assume. In the X direction, we ignore air resistance, which means there's nothing pushing this object left or right. So there's no net force on the object in the X direction, which means our acceleration in the X direction is 0. Since our acceleration is 0 in the X direction, that means in the X direction we are moving at a constant velocity. Okay. Now that can be very helpful to us when we need to think about graphs or think about calculating anything. So now let's talk about the Y direction. So in the Y direction, because this object is launched horizontally, the initial Y direction velocity is going to be 0. So initially in the Y direction, we are at rest. We also know that our change in displacement for the Y direction is whatever the height of the cliff is, h. Now again, the other thing that we know in the Y direction is something that we need to assume, or something that we can figure out. The only force acting in the Y direction is gravity. If the only force acting in the Y direction is gravity, that means the object is in free fall, so our acceleration in the Y direction is g, or negative 9.8 meters a second squared. And really, I should make this h negative since we're traveling downward. Okay, so X direction, Y direction, completely separate. As this object travels, it's going to travel in a semi-parabolic path. Okay. And that semi-parabolic path is because of the combined lack of acceleration in the X direction and acceleration in the Y direction. So let's talk about some things we can find for this object with the information given to us. So some things we might need to find are the time of flight, or what's considered the range, or the distance from the bottom of the cliff. Okay. Now, this time of flight is going to be true in the X and Y direction. Time is considered a crossover variable, kind of like mass. Range, on the other hand, is an X direction variable, since it's a horizontal distance. So let's say I wanted to find the range, right? Or I wanted to find my delta X. Okay. So because we're moving at a constant velocity, my change in X, or my range, is going to be my initial velocity times time. And that comes from the X equals x0 plus VIT plus 1/2 AT squared equation. If acceleration is 0, then my change in X is just the same thing as the initial velocity times time. So it looks like in order to find the change in range, or the change in X, I need to know this time. Since I can't use the same direction to find a similar variable, because this is the only equation I can use in the X direction, I need to go to the Y direction. Okay? Now, an important thing to keep in mind is that time is y direction dependent. Meaning, for a question like this, if you want to change the time the object is in the air, you have to change something about the y direction. So you have to change the initial velocity, you have to change the height of the cliff, or you have to change the acceleration due to gravity. So again, we're using the y direction to find time, and the only equation that has initial velocity, y, a, and t, is the same x equals x0, but just with y's plugged in instead of x, since we're in the y direction. 1/2 at squared. My initial velocity is 0. Okay? My initial position is a height h. My final position is the ground, 0. So I could rewrite this equation as change in y is 1/2 at squared. And again, I'm plugging in a negative h for that change in y. 1/2, right, negative g. I'm going to keep that negative out in front so it reminds me that it's down. T squared. Again, I'm using this equation to solve for t. So I'm going to multiply both sides by 2 to get rid of the 1/2. So I get negative 2h is negative gt squared. I divide by negative g. That's good. The negatives cancel, which I would have expected. 2h over g is t squared. Now if I want to solve for t, square root of 2h over g. So again, this is our time of flight, and that's going to be true in both directions, because if it takes me 2h over g seconds to fall that horizontal distance, then I have 2h over g seconds to travel horizontally. So once I have that equation for time, I can go back to the x direction. Okay? My initial velocity was the variable v times the time, 2h over g, and that would be my final answer for the range. Okay? Now, as this time over here increases, this range is going to increase. So some ways to increase the time, looking at my equation, is to change this horizontal height. So if I want to increase the time, sorry, that's not a horizontal height, it's a vertical height. If I want to increase the time, I would increase the height of the cliff. I would decrease the acceleration due to gravity, or I could launch the object upwards if I wanted. Now, one thing that's really interesting is, let's say we have a similar cliff with a height h. Okay? I have a blue ball that is launched horizontally off of a cliff, and a green ball that is launched, or rather dropped, from the same height. Okay? What's interesting is, as long as these two objects, the blue object and the green object, are dropped from the same height, they are going to have the same time of flight. Okay? Even though they have different horizontal motions, right? So this green object has no horizontal motion, whereas the blue object has some. Okay? Remember, horizontal and vertical, or if you want to think of it as x and y directions, are independent of one another. So if two objects have the same type of motion in the y direction, because time of flight is based on that y direction, they're going to have the same time of flight. Okay? And there are a lot of videos online that would show you this exact experiment. So you can look for dropped and shot videos. They'll be in nice slow motion, and you can see the two objects falling at exactly the same rate. So this blue object would fall in a nice parabolic path, while this green object would fall straight down, but they would both hit the ground at the same time. Okay? Now, they're not going to have the same velocity when they hit the ground, because this object will have a horizontal component of its velocity, but they will hit at the same time. So let's talk about that velocity just before you hit the ground. So I'm going to scroll back up to my example up here. Okay? Let's say I wanted to figure out the velocity just before I hit the ground. There's a couple of different ways we can do this. There's a way that you can do it using energy. So the idea that this object starts with some potential and kinetic energy, and you can set that equal to the final kinetic energy. But if you don't remember energy or you haven't learned energy yet, the other way of finding it is with kinematics. Okay? Now, as this object approaches the ground, it's going to approach at an angle because it will have some x component of its velocity and some downward y component. And those two components combine to give us our result in velocity just before we hit the ground. This Vx here is going to be exactly equal to the initial velocity we had when we were shot off the cliff, because there's no acceleration in the x direction. We're moving at a constant velocity. So this Vx equals v. Okay. Vy, on the other hand, depends on the y direction information. So let's say I wanted to find that final y direction velocity given the information about the y direction. So there's a couple of different equations I could use to find that final velocity. I could use v final squared is v initial squared plus 2a change in y, or I could use v final equals v initial plus at, since I know the time and I know change in y. So I like to use things without squared, so let's go ahead and use this equation. My initial velocity is 0 in the y direction, so that goes away. So it looks like the final velocity in the y direction is negative g, because that's the acceleration in the y direction, times the square root of 2h over g. Now remember, this negative just tells us that we're traveling downwards, so it gives us our direction. So Vy is g square root of 2h over g. Now the way to figure out what this resultant final velocity is to remember that those two vectors of velocity form the two legs of a right triangle. So the actual resultant final velocity is the hypotenuse. So that means we can Pythagorate or use Pythagorean theorem to find the final velocity. So I can use a squared plus b squared equals c squared. So let's say a is the y component and b is the x component, c is what I'm looking for. So we got to square root all of that. Oops, I forgot the squared there. So this is not going to be a pretty equation, but it's okay. So g squared 2h over g plus v squared. This g can cancel, so I have square root 2hg plus v squared is c. So that would be my resultant, or this v final. Okay. I could also use this triangle to help me find the angle of impact, or the angle that that velocity vector makes with ground or with horizontal. So if I know all three sides, I can use sine, cosine, or tangent. I personally like to use tangent because I usually know Vy and Vx. So the tangent of the angle is going to be that final y velocity over the x velocity. And I don't include a final with the x velocity because remember that x velocity is constant or the same throughout the entire path. So I have the tangent of theta is g square root of 2h over g over v, and then I could inverse tangent of both sides to get theta. It wouldn't look pretty, but that's what it would look like. So now let's talk graphs for a horizontally projected object. Okay. So velocity versus time graph. We have two different directions, so I need to use two different colors. Okay. So the horizontal velocity is going to remain constant at some constant velocity v, whereas the y direction velocity, which I'm going to draw in red, is going to increase as time goes on, and specifically it's going to increase in the negative direction. Okay? And the slope of this, if we're on Earth, should equal negative g, or negative 9.81. So we start at 0 and we end at some final y direction velocity. Okay? As far as position versus time, or distance versus time. Okay. In the x direction, because we're moving at a constant velocity, the x direction distance or horizontal distance is going to, that's not how you spell horizontal, is going to increase at a constant rate. Horizontal. Okay. And the slope of this should be equal to our velocity. In the y direction, because we are accelerating, we have to have a curve. Okay. So let's just say it's a distance versus time graph, so direction doesn't matter. Our vertical position versus time, or vertical distance versus time, is going to be a curve or parabolic shape. Okay. Now, this parabolic shape does technically show a positive acceleration, but again, I was saying that this is a distance versus time graph, so direction doesn't matter, meaning I'm essentially doing the absolute value of my displacement or change in position, which means all of my velocities, all of my accelerations, so they're all going to be positive. Okay. And that is it for horizontally projected objects.